Hello, friends of Trig. It's Alan here. We're all locked up trying to learn this radian measure, and now we're going to talk about the applications of it. So hopefully you understood what radian measurement is, how it applies, so now we can start applying it even more so to our problems that are going to look a little something like this. So in this section, we're going to talk first about how to apply all these radian measurements, and we therefore need to make sure that we understand what they are. So just a quick overview. One of the main things I wanted you all to make sure that you understood was the fact that pi radians is equal to 180 degrees. And if we know that, then we can use this pi as both 180 degrees as well as the real number approximately 3, a little bit more. Okay, so what we're going to be talking about in this section is first a little thing called arc length, and I'm going to go ahead and derive that formula with you all. And in order to do that, we're going to start with something that we reviewed last video, and that is the circumference. And so if you remember, the circumference of a circle is simply the perimeter of it all the way around, which is equivalent to 2 times pi times r. And so if we are looking at this from the center to any point, let's just go as if we would along the x-axis, and then say we wanted to rotate that, I don't know, straight up to the y-axis. Well, then we know that this angle right here would actually be 90 degrees. But what we're now going to talk about is the length of the arc and how we would find that. Well, so this is why I chose this particular one, because I know this right here is going to be that section of my circle. So we're going to use S for that. And we're going to call that the arc length. And so what we're trying to find is, instead of the entire length around, we call the perimeter of the circle the circumference, which we know is equivalent to 2 pi r. We're going to then take part of it, this arc length, S we called it, and we're going to take part of that whole 2 pi r. And how much of it? Well, right now you can see that's 1/4. Because if I was to extend this out, this would just be one of the 4 pieces to get all the way around that 360 degrees or 2 pi radian measurement. So we're going to multiply this by whatever amount we know of the whole angle that we'd be rotating it around. So in this case, just to kind of go through it with you, you know that that would have been equivalent to 90 degrees out of the 360 of our entire circumference all the way around, which would have been that 2 pi r. So I'm putting it over 1 because what I'm going to end up getting is a fraction. And so that fraction is actually going to end up being divided by 10, that'll drop the zeros, and we go into 9 into each of those to get 1/4. And so you can see that this is going to change, but what is not going to change is the fact that we're taking a part of the whole. So how could we say this in general? Well, there it is. And if we wanted to simplify that version, we could go ahead and cancel the 2, because all of this is multiplying. We can cancel the 2 with the 360 and say that it would be 180. But this is still ugly because we have fractions. We have a denominator down here. So what we all decided on was to think a little bit smarter and not have to work harder. We're going to say that the arc length, S, we're using it for that section of the circle, is going to be equal to whatever theta is, whatever that angle that we're going to rotate around, maybe pi, maybe something in between, 180, 220, whatever it might be. But it's going to be out of 360. But instead of using this as our formula, I'm going to replace 360 with its radian measure counterpart, which we said pi is equal to 180. Then if I double both sides of this statement, which is equal to one another, an equation, then I would get 2 pi is equal to 360 degrees, which means if I replace this 360 with 2 pi and I multiply it by the circumference, which was that 2 pi r to get all the way around, this, as you can see, works out much, much nicer. Because we're multiplying all of this on top and bottom, then I know the 2 and the pi can cancel to be 1s. And that leaves us with the s, arc length, is only equal to r theta. So that, my friends, is the derivation of the arc length formula. But we have to make sure that we realize that that cleaned up simplistic version only works when we are not using degrees, but what angle measurement. It has to be in radians. So the way that you can remember this is, yes, it is very cool. This formula is way nicer. It is rad. And it is so rad that we have to make sure that our angle that we use, if we're going to use that nice simplistic form of arc length, that our angle has to be in terms of radians. Okay? So be careful with that. Make sure that you're working through this when we do these with that in the back of your mind, so that you remember, yes, we are going to have to use radian measurement when finding the arc length. So there it is with the form already written out for you with the circumference, and again, us just taking a portion of it, some angle measurement to get that arc length. So how much of the whole is what we're really looking at. And because we can go ahead and multiply and just get r theta, that is the formula that we can then use to find a length, a part of a whole circle we call the arc length. So again, put it a bunch of different places, trying to make sure that you know if you're going to use this, it's in radians, not degrees. So make sure you have a note of that somewhere. So what we're going to look at now is how we can do that in a similar form, but now instead of finding the length of an arc on the outside, what about the inside? And hopefully you all remember that the area of an entire circle is equal to pi r squared. So just like the last form, this will find all of that space inside, but what we want to find is just a section of that circle. And so therefore we are going to call it a sector. And we're going to find the area of one of those sectors. And the area of that sector would be completely dependent on how big of an angle, the size of that sector, which is dependent on the angle that we open this up to. So if we wanted to just draw this line straight over and find all of this area, then we know that we would take half of that. And unfortunately, you can see nothing really works out to cancel. Okay, but here's the nice thing. Is it always going to be half? Absolutely not. So we know if we only want that little section, it is going to be dependent on two things. Well, the pi r squared will give me the area of the entire thing, all of this. But if I only want a part of it, a section, then I'm going to have to multiply that by whatever fraction, whatever part of my whole that I'm going to have. And as you saw in the last one, yes, we can use 360 as our degrees, but now you're starting to see in this chapter that the degree measurements is not always the best. So we're going to take that 360, which, yes, we could go all the way around in that 360 degrees to get the entire pi r squared, which would just make this whole thing a 1, which is why this also works for area of any circle. But we want just a part of it. And that part is therefore going to change from 360. We're going to use the equivalent, which is 2 pi. Because again, we're trying to make this look a little bit simpler in form. And since 2 pi and 360 are the same, just different way of measuring an angle, but represent the whole thing all the way around, notice that allows us to actually cancel some things, which for us works out really well. Since all of this up top and all of this in the bottom are multiplying, I can cancel the pi over the pi and get 1/2 times our r squared times the theta. And we typically write the r squared first and then the theta last, because we want to make sure that you understand the only thing that is being squared is r. So our next equation that we have to memorize is for the area of a sector or section, part of an entire circle. And we said that that would be 1/2 r squared times theta. But again, that only works if and only if we are using what for theta? Radian angle measurements. Okay, so keep working on this. That's pretty much it as far as the derivations go. To make sure that, again, you have that there. There it is for you. Trying to once again hit home and point out that yes, indeed, you do have to make sure that your theta is in radians when working with this. Okay, just like we saw for arc length, must be in radians for both to use these specific formulas or equations. But they're asking us to find a rope that's being wound around a drum with this size of a radius. How much of that rope will be wound around? I don't know why they put these tongue twisters in. If the drum is rotated through an angle of 39.72, and I put the graph here below. So again, whether we start it north like this or start it over here and rotate that 39.72 degrees, either way, immediately you should see that there are 4 sig figs. Okay? And when dealing with this, if we want to know how much of this rope that we're going to have to cut, just this section, which means we're looking at an arc length. So again, what are we trying to find? Well, remember, we're dealing with how much rope will be wound around the drum if the drum is rotated only by that angle there. So in order to figure out just this section of the rope, how much of it that we will need, then we're finding arc length, which means this once again. So our r times our theta, and the cool thing is they pretty much flat out told us the radius is this and the angle is this. So we will go ahead and punch those two things in, being very careful to remind ourselves. Hopefully I've done enough examples with you guys to make sure that you are also paying attention that you need radians, not degrees. But it's no big deal. We've worked on that since the first chapter and pretty much the first section. In order to get rid of that, we would just multiply by some fancy looking one of pi over 180 degrees in this chapter. Okay, so again, just multiplying all of that out, pretty simple to do, but the length that we would have gotten that rope to be for the 39.72 rotation of it would be, and if you got that, just make sure to give them the answer that they wanted it out to in either the first, second, third decimal place or whatever. And if they don't specify, then use the sig figs, the least amount that we're given, in this case 4. So 1, 2, 3, 4, we got to look to this to round. So we will say 0.6049 what? Well, remember, these would cancel out, and we don't need to ever write the radians, so the only unit measurement that is left would be feet. So hopefully you're getting the hang of this. You're seeing the little nuances multiplying by that pi over 180 to get rid of degrees, and making sure that we're in radians.